Okay, so here in our first podcast of Unit 2, we're going to be talking about the historical development of atomic structure. Kind of how do we know what we know about the atom, and how did they figure that out over the years? So one thing that's not going to be included in the notes that I insist that you write down for about each of these discoveries and people is the dates. So I went ahead and I just kind of included this little timeline here to give you an idea of when all of these things were happening, but we're going to be more focused on the actual discoveries and the process of making those discoveries. So let's jump in with this Democritus guy. He was an ancient Greek philosopher, and he was the first guy that came up with the idea of the atom. The Greek word was atomos, which meant uncuttable or unbreakable. So he came up with this idea of atomos, that eventually every substance is going to reach a smallest, indivisible, uncuttable piece of matter. Other scientists at the time just thought, oh, if we get a better knife, a better tool, we can always keep cutting things, breaking things down farther, that we could keep going down into infinity. But Democritus said, no, there's got to be a point where we stop. And now we call that point, the smallest piece of matter, the atom. And Democritus didn't really do any true experiments, especially not compared to some of the more modern day scientists, but he based his ideas on observations of everyday life, that everything was made of smaller and smaller pieces and parts. And if you took something like a shell or a rock, you would eventually get, and if you broke it in half over and over again, like what's shown in this picture, eventually you would get to the smallest piece of that rock or of that shell or of a piece of cheese. And whatever that smallest piece is that you couldn't cut any farther is what he thought was an atom of that substance. So he thought the atom was a solid, homogeneous sphere made of the original substance. So a shell would have shell atoms, stone would have atoms of stone, cheese would be cheese atoms, just small homogeneous spheres of the substance, just in its smallest particle that can no longer be cut. So pretty simple idea of the atom. And even 1,000 years later, when we get to Dalton, and we're only going to fill in the Dalton half of this table real quick, when we get to Dalton's atomic theory, he actually hadn't developed or come up with any new model of the atom that was different from the ancient Greeks. He's still assuming that the atom was a solid, homogeneous sphere. But he came up with some rules for how atoms are going to act and react with each other based on how he studied some gases. So the rules that he came up with is really what we need to focus on writing down here. And his first rule, this might seem obvious, we already said this earlier in Unit 1, all matter is composed of very small particles called atoms. So all matter is made of atoms. Everything is atoms. Secondly, all atoms of an element are exactly the same. You can't tell the difference between two different carbon atoms. They're both identical. They got the same stuff making them up. Thirdly, atoms cannot be created or destroyed. They're indivisible. Coming back to that ancient Greek idea of atomos. That atom is atomos, uncuttable. 4, atoms can combine with other atoms in whole number ratios. Like, think about the formula for water, H2O. We could never have a formula for any compound that was like H2.1O 3.5. We can't have those decimal ratios. We had to have whole number ratios. And finally, in a chemical reaction, atoms are rearranged, not created or destroyed, just rearranged, moved from one place to another. So that was what Dalton added to our understanding of the atom. Like I said, not a new picture of the atom, but because of some very detailed experiments, he started to get us better rules for understanding how atoms act. And that kind of opened the door for some of these next scientists, even 100 years later, to come around and make some key discoveries. Now, these discoveries you see on the page, it says, explain how the electron was discovered, nucleus, electrons. So in each of those spaces, make sure that you get down the scientist name that made that discovery, the experiment's name and a little summary of it, and the atomic model's name and kind of summary of what it looks like. I'm going to have a lot of information on these pages, including a bigger version of those pictures that you have in your notes. I don't need you to get every single word down, but I need you to make sure that you're getting these key ideas, because these are the things that we might ask you for on tests and quizzes in the future. So, explain how the electron was discovered. Well, the guy responsible for that was Thomson. I have seen this name misspelled with a P, but most of the references I find have no P in that Thomson. And, well, what did Thomson do that helped us discover the electron? Well, the experiment was the cathode ray experiment, so make sure you get those words down. And a cathode ray is actually the same thing that used to be in the very back of those big old TVs, like not a flat screen TV, but the ones that were like 2 or 3 feet deep that we almost never see around anymore. Well, there's a cathode ray in the back of it that shined at the front screen and lit up the screen so we could see it. So back in Thomson's day, those cathode rays had kind of just been discovered and everyone was playing with them because they were so cool. They created these beams of light. And he was the one that realized if you shot this beam of light through some magnets, then the beam always bent towards the positive side. You can kind of see that here in the middle of this diagram. The beam started bending towards the positive plate. And even when he moved things around, no matter which orientation, it wasn't just always up or down, it always bent towards the positive plate. And they knew at this point that opposite charges attract. And so that must mean that the beam was made of negative particles. So that's how he discovered the electron. He actually called them by some different name at first, but now we call those negative particles in our atom the electron. And his model of the atom was called the plum pudding model, because he just imagined, okay, we have that solid sphere, just like what the ancient Greeks were thinking, but since I discovered a little negative particle inside the atom, then I'm just going to leave it as a solid sphere with some little dots around it. And over in Great Britain, plum pudding is something that they eat all the time. Here, not so much. So you might just think of this like a chocolate chip cookie model. Think of the dough as a big positive mushy part of the atom, and all of the chocolate chips are the negative electrons scattered throughout. So it was kind of randomly arranged, and he knew there still had to be positive stuff in there because there was no charge when you looked at an atom on its own. So if he discovered there was negative stuff in there, there must be some kind of positive stuff canceling it out. So that was his reasoning. Still pretty simple, but he discovered an electron, so he started shoving those electron chunks into the atom. Now, he wasn't quite right. The next thing that was discovered about the atom was the nucleus, and that was discovered by Mr. Ernst Rutherford. And Rutherford's experiment is called the gold foil experiment. So make sure to get down that he was doing some experiments with gold foil. And he shot positively charged radiation at this gold foil. And the foil is super duper thin. This radiation is pretty strong. And so most of that radiation did go straight through because it had nothing to hit. Most of that gold foil, even though gold is so incredibly dense, most of that foil must have been empty space if most of that radiation went straight through. But not all of it went straight through. There were some particles that bounced off of the gold foil and hit at some weird angles, not just straight through. So there had to be something in that atom, or in that foil, and the gold atoms that were in the foil, for that radiation to hit and bounce off of, but it must be super duper small because it's not, most of the radiation isn't hitting it. So because some bounced off and the radiation was positive, he knew that the particle, the thing that it hit, must also be positive because positives repel and would bounce. If it was a negatively charged particle in the middle, it would have stuck with that positive radiation. So because it bounced off, we knew it was positively charged and had to be dense enough to make that radiation bounce. So because of that, Rutherford came up with this new model of the atom, which is called the nucleus model, which basically takes all of that stuff from the atom. Instead of being a solid sphere, the sphere of the atom is actually mostly empty space. And this is not to scale. That nucleus would be just a teeny tiny speck, even smaller than this red dot if we had it to scale. But basically, it's mostly empty space. We've got this dotted line edge around it because it's not a hard shell. It's just general area that the atom claims as its own. So we have that small positively charged nucleus with electrons scattered around in this empty space. But even Rutherford wasn't correct, and it was actually one of Rutherford's students that ended up figuring out how those electrons are arranged. They're not just scattered randomly in that empty space. And his student's name was Bohr. And Niels Bohr discovered that electrons are arranged in predictable orbits around the nucleus, and he called those orbits energy levels. And we're going to talk about his flame test that he did in a lot more detail at the end of this unit, and then after we test, we're actually going to do the flame test in order for you to be able to recreate this and observe some of these patterns that he saw. But he was basically burning elements and looking at the pretty colors that was released. And he was actually making some pretty precise measurements of the energy that was released. And what he saw in his measurements and in the colors was that there were specific kind of lines or bands of light that were being produced by a given element, and then there were these gaps in between those lines where he wasn't seeing any light being created. And every different sample that he burned of the same element gave the same kind of characteristic fingerprint of lines and bands of light and darkness. And so when he saw that only certain colors were produced, and it wasn't just a continuous full rainbow of color, he realized, well, since the light comes from the electrons, if there's only certain energies of light being produced, then there must only be certain energies of electrons in this atom. So then we call those energy levels. Those stable orbits are the level of energy that the electrons have. And every element has electrons at specific levels. So that gets us this model we call the planetary model, which kind of looks like the sun at the center of our solar system with the orbits of those planets around it. And so Bohr thought, okay, we've got these energy levels like the orbits of the planet, and our electrons must rotate around on these energy levels because they only have specific energies if they're only giving us certain energies of light out. Now, there is a lot more information, like I said, that we'll talk about how he did this and exactly what is happening with those electrons, but we'll get to that later in the unit. Bohr's model, even though it's not perfectly correct, is probably one of the best ones that we have that's still simple enough for us to understand, so we still use it and talk about it a lot in class, even though it is a little bit dated. Now, we're going to jump back up top, right next to where you wrote that Dalton's atomic theory tenets, those rules out. We're going to fill in these last couple of things about what we know and understand here in modern atomic theory. And sometimes we call this the electron cloud model. This is just currently our modern theory of what the atom looks like. And you don't have to draw this, but we'll get more and more into this idea of the electron cloud and these different orbitals that the electrons can live in, because it's not nice, simple orbits that go around like the orbits of the planets around the sun. They're a little bit funkier looking, but we'll talk about those shapes and clouds and orbitals later. What's most important is that now, in our modern atomic theory, we don't actually agree with all of those rules that Dalton came up with way back at the turn of the century. So if we look at each of those, we do still agree that all matter is composed of small particles called atoms. But one of the things we're going to start by talking about next class is not all atoms of a specific element are exactly the same. There can be some differences. And hopefully you remember a little bit of your middle school science. Atoms can be created and destroyed. We do have that technology now. Dalton just didn't have that back in the day. But atoms do combine in whole number ratios like H2O, and when we react atoms, they just rearrange. They're not created or destroyed in reactions, even though they can be created or destroyed in other places. So I do want you to copy over those 3 rules that we still believe in over here, and just kind of understand we've had more technology nowadays than Mr. Dalton did back then. So that's it.